So shall we start? We go back to yesterday's lecture, and we start again with the how the energy deposited into liquid noble medium is then converted into something that we can use for our detectors. So here we start with the deposited energy, okay, and that can induce both excitation or ionization, as we said. So if we have excitation, then this leads to the emission of photons, ultraviolet photons that we can detect. What about ions? We have electrons, but this means that if the electron is get free, then we can collect really the electrons. Otherwise, there is the certain probability that the electrons will recombine with the probability R. But this again shifts us into the excitation channel. And so with the probability R, the liberated electron will anyway produce a new UV photons. Otherwise, with 1 minus R, we will have the possibility to use free electrons to collect the signal. So now this turns out to be linear into the deposited versus the deposited energy if we consider the sum of the two channels, and this can easily seen here if we assume that the total number of quanta is equal to the deposited energy divided by a certain a certain number, that is this W, that in the case of xenon is about 13 electron volt. So this is the total number of quanta generated, and so this is equal to the amount of particles into the excitation channels plus the number of ionized particles. Now, for the final state, the number of photons is equal to the number of direct excitations, so those that goes directly into this channel, plus R, the number of ionization, so the ionization electrons which recombined. On the other side, the number of electron that is also called NQ in some of the notation is then 1 minus R times the number of ions, okay, because these are just the electrons which did not recombine. And clearly, if you now sum these two ones, you get a cancellation, and so again this is equal to the number of photons plus the number of electrons. This is fully true for electronic recoils. So for electronic recoils, we have this linearity between the energy deposited and the sum of charge and light. We can use this in a very powerful way. Now, forget about the S1 and the S2. We will come to this in a moment, but just consider that S1 is the signal that we have in our detectors associated to the light channel, while S2 is the one coming from the electron collection. Okay, I just need to anticipate this notation, but in a few minutes it will be more clear. So, for instance, you see that if we now have the energy deposited by a fixed energy line, as we have in case of many calibration signal, many lines, and so on, and if we plot it in the plane of charge versus light, this is what this plot is telling us, we have this ellipse that is anti-correlated in the two signals, because the more is the light, the less is the charge, and vice versa. And this can be seen in many of these plots. Energy is constant, so the energy of this ellipse is coming from a single line at a fixed energy. But each line has this elongated shape in the given by the anti-correlation of the two channels. You see also here, this is for other lines. The point is that at the end, if we can collect properly the signals, we obtain a very good energy resolution. That is, okay, it is linear, and this is one point, but also the energy resolution is very good. Just to keep a number in mind, we obtain less than 1% at the MEV scale. And this is relevant, for instance, for double beta decay searches, where the Q value in xenon is 2.5, 2.45 MeV, so at this high energy. Now let's see some other plots of this kind. This is indeed what we call the Doke plot, this linearity or with the anti-correlation of the two signals. And this is an example that we made with xenon 1 ton, so our previous detector, where you see that each of the line lies in this anti-correlation lines. Why they are not in the same point? Because for each different energy, there is a different fraction of charge and light due to the mostly due to the d over dx of that particular line. So you have different gamma energies, and so different electron, Compton electron energy, and at the end you have a shift along this line, but each of them has this anti-correlation, and so you can reconstruct the energy very well.
Why you have this? So the ellipse should be like the width of the line, say, or the width of your energy resolution.
Right.
Why you have this?
This is
wave.
This is the Compton tail, because you use a fixed energy calibration source, so you have your cobalt with 1.3 MeV. Most of the signal are due to the photoabsorption, but you still have some Compton. Yes, so you have a tail at lower energy, but you can determine very well the peak, and so use that.
The atom instead of being absorbed.
This one, yes, exactly. While this is the full absorption peak.
Then when people look for like absorption of dark matter, shouldn't the spectrum also look like this? But it could be metaphor.
Well, yeah. The rate is like, the point is that then you have, so here is QED, so you have a lot of rate, so the phase is C.
No, you don't need the photon, just the QED. No,
but with the, okay. Now, just to show you, this is the Doke plot in the recent detector, and here we have many lines, but the amazing point is that we go from the 2.8 keV of argon-37 here in this island up to 4.4 MeV of the gamma emitted by the americium beryllium source. So in the whole energy range, there is this linearity that is extremely good and powerful. Now, that is for electronic recoil. So linearity in electronic recoil. What happens with nuclear recoils? In this sketch, basically, we have again the scheme that I put on the blackboard. Mostly in the previous scheme, we only looked at the two lines here. We have to consider that there is a channel going into heat, and with nuclear recoils, we have a higher population of energy that goes into this channel. So it's basically invisible to us because we only see light and charge. In an argon or xenon detector, we cannot detect the heat as they do in bolometers. Paolo will talk a lot about this tomorrow. For nuclear recoil, so we have this so-called quenching, which simply means that when you are here and you estimate the total number of quanta that you have, this is not just a simple relation of the energy divided by the typical energy needed to create one quanta, but you have a scaling factor that is this Fn. That is 0.2, 0.1, it depends on the energy and so on. But just again, to keep in mind that in the case of nuclear recoil, you basically have 1/5 of the possible signal in your hand. So this is a first consideration. The second one is that since the recombination here depends on the electric field, but once you fix the electric field, it depends mostly on the specific energy deposition. In the case of nuclear recoil, you have in general a higher d over dx, as you can see also from the microscopics of this particle. This is an alpha particle in 10 nanometers, while fast electron is here in the range of 10 micrometers. You have higher dA over dx, higher recombination, and so a reduced charge signal compared to the light one. And this is what we use to discriminate between electronic and nuclear recoil, in particular in xenon detectors. So now I need to skip some of the slides due to time constraint, but just to flash you that there are a lot of measurements done specifically on these points that I made, because it's crucial to determine from the experimental point of view all these fractions that I mentioned. So how these measurements are done, probably this could take an hour of a lecture, but these experiments are extremely tricky because you use very small detectors. You start with known fixed energy particle, either neutrons or gammas, to reconstruct fully the kinematics, and then you go to a certain angle detecting the particle. In this way, you can track the kinematic of the scattering, and so basically you know the energy of the recoiling either nucleus or electron in the case of a gamma. And inside your detector, you measure the charge and light. And this is a powerful but tricky way to obtain all this information that are present in our formula. I put here many ways to do this. This can also be done inside large-scale experiment, as here in LUX, where they used monochromatic neutrons and looked at double scatters inside the detector. Again, Laura did this beautiful experiment in Zurich to characterize electronic recoils and also with light charge. In principle, you want light charge, you want to change the electric field to parameterize all the possible configurations. Right.
Yeah. No.
This one?
Yeah. I mean, about the speaking function that you're using.
Here.
People are using. How is it possible that it doesn't go down like
Why? Because this is the specific, this is called the charge yield. So it's already divided by the energy. Why it has to go down? Okay. It's not the absolute, the total charge emitted, but it's the charge per unit of energy, or correspondingly the light emitted per unit of energy. So in principle, it doesn't go to zero even if you go down in energy, as soon as you have some energy to put in the system. This is done in liquid argon detectors with extremely small lines of argon-37. So you see that we can characterize a very large range. And this is just to tell you that there is this tool called Nest that you can access at this website. You can also play with it. A few years ago, there was also a easy to use Excel version. Now you have the code to download, you can plug it inside your Giant 4 and so on. Anyway, this nest simulation can be used also during these days if you want. And basically, for instance, in the website, you put your input, you select the particle, the density of the medium, so xenon or argon, the drift field, the recoil energy, and you obtain the number of photons emitted, the number of electrons, and so on. You can also do more, adding also the characteristics of your detector, but this is an additional step. In principle, this is a proper tool that predicts the light yield and charge yield. How it works, there is a model, the model that I mentioned, but more important, it is filled and fitted with all the data that I very quickly showed you. Okay, so this is what you can do, and we will not go through the various plots, but just to show you that you have all the possibilities. Yes.
Yes. Yeah, so I see, so so I mean, so
This
the
is
number of quanta, this is the number of quanta per unit energy.
per unit of energy. Here, quanta means light, in the case of the blue one.
It's binary, it's constant.
For electronic recoil, yes, due to this relation here. While for nuclear recoils, this is not fully true. It depends on the energy. And you see that the anti-correlation is clearly visible in the electronic recoil channel in particular.
Zero dissipation.
Right, down at least down to 0.2.
This thing is, doesn't lose energy.
The one that goes into
Yes, but it is lost, and this happens mostly for nuclear recoils. For electronic recoils, down to the 0.2 keV, it is proven that you are linear, and so you can reconstruct 0.2 keV. That
That I go to very low end. So at some point, I will cut the material.
Mhm.
It's just enough to be nothing there.
right.
Because it's not to fight with these ionic light. Yeah.
Yeah, exactly.
Okay, so
You need to produce charge or excitation at some point. So this 13 electron volt.
making some of these electron free in the xenon. Yeah.
This is the W. This is 13.7 electron volt in xenon. Or 11.5 as they measure. There is some tension nowadays. Anyway, slightly more than 10 keV. But if you go below that, of course, you're not linear anymore because you cannot produce your carrier of information. Okay. So now, just I will leave this in the slides so you can play with Nest if you want. Now let's move to something closer to a real detector, because I spent a lot of time to tell you how argon and xenon emits light and charge, but at the end we want to collect these potential signals. And first of all, we want to drift the electrons up to a region where we can collect. Due to the characteristics of the noble liquids, the drift velocity, so the velocity that the electron gets when we apply an electric field, is of the order of millimeter per microseconds. Okay, so this is another number that you can keep in mind. For instance, consider that now the current detectors have a size of meters, and so we need to wait milliseconds, a few milliseconds to collect the signal. This is important. This is what I mentioned, saying that these kind of detectors are slow by definition. There is also the diffusion that matters, but in the case of this media, it is quite small, millimeters over 1 meter. This is again important. There is a diffusion in the longitudinal way, but also in the transverse dimension. And of course, if you want to reconstruct the position of your event, this is a key parameter. Anyway, we are here at the order of millimeters. What are the enemies? Indeed, we have emitted light and emitted charge. To collect them, since we are not inside the medium with our sensors, we need to clean up the system very well, in particular against water for light. Water is the worst enemy for light absorption. On the other side, for the electrons, all the electronegative impurities can be avoided, has to be avoided, and in particular oxygen, okay? Of course, this is something that has to be done continuously, okay? There is some baking, real baking, that you can do at the beginning, in particular for stainless steel. So you really heat up the detector before putting the xenon or the argon in order to get out all the water, the oxygen, and so on. But some of it will be trapped and be re-emitted. So you need a continuous purification system, also because, even because the amount of impurities that can kill you is extremely small. Just to give you a few numbers, with 1 ppm, 1 part per million of water, we have an absorption length of 40 centimeters. Again, consider that we are aiming at building a meter size, multi-meter size detector. So this is too short. We want to be definitely better than this, such that the light, the precious light that has been emitted, can be really collected. In the case of charge, it is even worse. 1 ppb, 1 part per billion of oxygen equivalent can give you, this is expressed in terms of electron lifetime. That means the time after which the electron cloud is reduced by a fraction by 1 over E. And this is about 500 microseconds. I told you that the drift that we need is order of milliseconds. So again, we need to do better than this, otherwise our electron cloud that is generated will be reduced very much before reaching the collection point. So these are the challenges, and these are faced with continuous purification of your target. This is the sketch done in Xenon 100, where we took out the vapor xenon from the top of the TPC, put it into getter, then liquefy again, and put back in the detector. Yes.
Electrons are moving after the speed of light. No.
No, the electrons
They are slow.
are millimeters per microseconds. The drift field,
Ah, okay.
millimeter per microseconds here. Sorry. So the TPC, the size of our detectors, is now of the order of meters. That's why we need milliseconds to get the electron. And that's why with 1 ppb, you have a typical killing. Yeah, exactly. So your signal, your precious signal is gone if you don't purify fast enough. And you have to be fast because oxygen, in particular, is continuously released. And so this was the system in Xenon 100. This is the one in Xenon 1 ton. And this is the one in Xenon N ton. So we increased complication. In the case of argon, it's quite similar. So this is what is needed to make these detectors work. Now, let's go to see the characteristics of the detectors, in particular of double phase TPC, and then mostly I will show you some results, in particular on the performances of the current generation detectors. So this is how the various kind of liquid noble detectors, single phase detectors only use the light channel. You see that in general they're made, they're fully covered with a 4 pi coverage of photosensors. Single phase TPC like Dune or Icarus, where you have the liquid and you collect, you both see the light, but in particular you collect the electrons through these wires at the end of the drift region. And we will focus mostly on double phase TPC. Right, so I left the slides with some description, but I prefer now to show you this animation that in general is helpful. Let's see if it works. So what are the ingredients for a double phase TPC? You need a pot, you need a cryostat, something to contain the noble element and to cool it down. Indeed, you can fill it, cool it such that the medium is now liquid, and playing with the pressure at the top, you can have a gas pocket in the upper part of the TPC. Okay, so this sketch was done for xenon 100. You see here the dimension of 30 centimeter times similar amount. Again, now we are playing with 1.5 meters, 1.5 meters. Okay, first of all, you have the medium inside the cryostat. Then we can apply an electric field. We have 3 main electrodes. We will see that there are more, but the main ones are 3. We have a ground one that is placed just below the liquid level. There is a cathode at the bottom. So the cathode is inside the liquid phase, very close to the bottom of the detector, and the anode on top in the gas phase. The third ingredient are photosensors. Okay, we need to collect the signal, and so we have 2 arrays of photosensors. One is at the bottom, inside the liquid phase, and a second one is in the top part in the gas phase. The from the picture here, from the sketch here, you cannot see, but clearly the photosensors are looking inward. Okay, so because the light comes from the inner part of the detector. Now let's see what happens in such a TPC. When we have an interaction with the nucleus of the detector, this is the sketch of the electric field. When there is the interaction, here it is, there is first of all excitation and emission of scintillation light that is seen by the photosensors, and we have a first signal. You see that the electrons are drifted up to the gas phase. Here they make a second light signal that is again seen in particular by the top array of the photomultipliers. Now we will see it again. So first I tell you again and then we will see. Interaction. There is the prompt emission of light through excitation or recombination, but anyway, scintillation light, and this is detected by the 2 arrays of photosensors. This is the S1 signal, the first signal called S1, as it was already indicated here. S1, the first one, is related to the scintillation signal. At the same time, electrons are now liberated are free from the atom. There is the electric field, so they move upward with this slow velocity, so millimeter per microsecond. After some time, say after 1 millisecond, they reach the gas phase. Here there is a second electric field that is larger. It is enough to extract the electrons from the liquid to the gas phase and accelerate them in the gas. With this acceleration of the electrons in the gas, there is the continuous excitation of the atoms of the gas phase, and this leads to a second light signal, okay, that is identical, so the characteristics are identical of the emission of scintillation light in the liquid. Same wavelength, same time constant, and so on. So it is true that both are light signal at the end. Indeed, we only detect, so we detect both of them with photosensors. But the first is related to the scintillation light. The second is related to the amount of electrons that reach the gas phase. In this way, we can clearly see both signal because they are well separated in time, and know which is related to what. So let's see again the interaction. First emission of light. Light bounce and is seen by the photomultipliers. The signal is there. The electrons goes up, move up slowly, are accelerated in the gas excited, the light is emitted, detected, and we have a second scintillation signal. How can we use this information? So, for instance, the time difference between the two signals is a powerful determination of the Z, of the depth of the interaction, because the time difference is related to how deep is the position of the interaction in the detector. Here you have the formation of the waveform, where we have the first signal here and the second signal here. Let's see it again. So prompt emission of light, and we have the signal. Electrons takes a while to reach. Now there is the second signal. So this time difference can be measured very precisely, and knowing the drift velocity, we obtain the Z position of the interaction with a very good resolution, below the millimeter in particular in this detector. What about the other coordinates, the one orthogonal to the vertical? They can be reconstructed if you make your photosensors array properly. For instance, having many small photosensors, then you can reconstruct the center of gravity of the light detected. Because, and this is done with the second signal, mostly, because in this case, the electrons move vertically, they reach the gas phase at the top. Let's see it again. They reach the gas phase, and the light is emitted in the gas pocket, so very close to the top PMT array. In this way, the cone, the solid angle seen, is focused quite in a small position. In the example that we made here, there were two clouds of electrons, typical of a double scatter event. And so this can be used also to determine if the interaction is a single scatter or a multiple scatter. You may remember that yesterday this was one of the tools to distinguish between signal and background, because from the WIMP we do expect only a single interaction. So we want only one of the islands that are here. Clearly, this is a double scatter interaction. I can reconstruct the position of both, and also say that this is not a WIMP. This is not a WIMP candidate because it's a double scatter event. It may be due to gammas, making two Compton scatters, or to neutrons, if they make two elastic scatters with the xenon nuclei. So in this way, I can reconstruct fully the position of the interaction inside the medium. And so I can use the fiducialization that we mentioned yesterday, because WIMPs are expected to interact uniformly in the volume, while background is expected mostly in the outer layers. So the position is very important. The capability to distinguish single and multiple. Plus, we also want to have particle discrimination, and this is done through the ratio of the S1 and S2 signal. Usually, we use the ratio S2 over S1, that is related to charge versus light. And the one of nuclear recoils is smaller than the same ratio for electronic recoils. And again, because with higher recombination, the S2 signal in the case of nuclear recoils is smaller and more energy goes at the end into the light signal. This can be checked with calibration sources, and this, for instance, was done here. You see that there are these two bands that in the case of xenon are somehow overlapping, and one can use, for instance, a gamma source to reconstruct the electronic recoil band, or and neutron to reconstruct the nuclear recoil band. So in this way, you have the characterization of the two kind of interaction. And so again, this was the table with the various backgrounds. I stop just 1 minute to see if this is clear, in particular the characteristics of the TPC. And yes, any questions on this?
So just to circle back to what Nick was raising before, the inefficiency arises from the fact that you don't always measure all of the N gamma and NQ, basically, right? This is the dissipation, essentially, the fact that you can go through it, right?
Right. So there are various points. So in terms of the light, okay, you have this light generated. Then there may be some absorption inside the volume, and this can be helped with purification. But also the walls of the TPC have a certain reflectivity, but this is not 100%. We use we will see. We use PTFE. That is a very good reflector for the ultraviolet light of xenon, but there is a certain fraction that is lost. The same for the charge, where here the key point is the oxygen, and so the fraction of electrons that are lost reaching the top. There is some loss also in the extraction phase. When you are in the gas, you are done. Then there is the multiplication. Indeed, we can see the single electron, because each electron produces about 30 detected photons in the S2 signal. So it's really a strong signal and well separated one from the other if they arrive. Indeed, we have a paper with the results also on a few electrons signals. Okay, see. It is useful because it's one of the 3 coordinates that you need to understand, to reconstruct the position of the event. Yeah. We need to know the position to find backgrounds, because if this is our detector, WIMPs have a uniform probability to interact, but the backgrounds, in particular, the background from the outside, will be mostly in the outer region here. So in general, one selects a fiducial volume in the middle of the detector to get rid of the background from the outer layers, and so the position reconstruction with a proper precision is key. In general, yes. Yes. So the cut, of course, now then there are the details of the analysis. The cut can be made in a strict way. So you really cut out the outer layer, or you give different weights to the various regions. So you can also play a little in a more clever way. But in general, at least the very outer layers are cut out, because the materials, so the stainless steel, even if you checked, you selected the best one, is anyway a source of background. Another unavoidable source of background are the photosensors. PMTs have metals, quartz, and so on, ceramic in the stem that lead some backgrounds. And they are directly in touch with the xenons. They are very close to, of course, because you want to collect the signal, so you have to be there. It's always a compromise. Okay, so now let's go back to the other. Okay. So here in words, what I mentioned for the discrimination. So you can use the S1 and S2 in particular in xenon detectors, and with argon detector you use also the pulse shape discrimination. Yesterday we mentioned it. I just summarized here the two capabilities. Indeed, at the end, while for xenon detector, at most you have a discrimination power of 10 to the third, with argon detector, you can go up to 10 to the 8, but you need light. So the price to pay to have this very good discrimination power is to be high in threshold. You need at least 30 photoelectrons in S1, so in the first signal, to be powerful. Okay. Now let's go and see some real detectors. Here we start from the argon world, and this is a sketch where there is the evolution of this kind of detectors in the last 15 years. Basically, most is done inside the dark side collaboration, where they had a detector at LNGS of 50 kilograms. And now they are building a 20-ton detector that is mostly a 50-ton detector with 20 fiducial. We will see some details now. Okay. Indeed, these are the two programs. Also, the shielding is completely different. DarkSide 50 was inside a water tank, a 10 meters by 10 meters water tank, and it had an additional layer of liquid scintillator doped with boron to act as a neutron veto. Okay. Neutrons are dangerous backgrounds, and so they used this tool to reduce the backgrounds from neutrons. The TPC was inside this cryostat, the small one, at the center of the detector. You will see many of these onion structure detectors. For DarkSide 20K, for the next version, of course, the TPC is much larger, and we will see the details, but also the shielding is different. Everything is done in argon. Then we'll come to this in a while. So just a few results from DarkSide 50. This was extremely useful to prove that you can use underground argon to decrease the electronic recoil background in the detector, and also to check the discrimination power, in particular of the pulse shape discrimination. Here is their data taking. You see that basically everything was electronic recoil in this band, while this island here is where they would have expected nuclear recoils. That is clearly well separated from the other region. They didn't see any event over there, so they put an upper limit. The limit of DarkSide 50 was not competitive with the xenon detectors at the time because of the size. There was 50 kilograms of argon compared with the tons, for instance, of xenon 1 ton at the time. But it was important to prove the technique, and so to pave the way for the next detector, the one that they are building right now. There was another important point that is summarized here. And I told you that we want to use both signal, the light and charge signal. This is still true, but if we want to reduce the threshold, and this is something that is useful to detect, in particular, light dark matter, we can give up to the light signal because the light signal is the weakest of the two. Okay. What happens if we give up with it? Well, we can go down in energy because we still have the charge signal and we can see also few electrons, so we can go very down in energy. We lose in many of the characteristics that I mentioned. Sorry. So if we don't have light and charge, we cannot reconstruct the position of the particle very well. We can only do the XY, but not the Z. Also, we cannot discriminate between electronic and nuclear recoil because this is done by the ratio S1 and S2. So we have to give up to many tools to fight background, but we gain in the energy threshold. So if somehow you can have a good compromise between these two points, you can go down in energy. And indeed, Dark Side 50 had a very clean result that was the best limit in the region between 1 and 3 GeV. So where, for instance, xenon detector with the full S1, S2 analysis cannot go because at this mass, we are below the energy threshold of the xenon detectors. Of course, also with xenon, you can do the same, and we did. Somehow, Dark Side was made with plastic detectors, no electrodes, so electrodes were made in another way, and so the signal was very clean in their case. Now, let's go to the big detector. So they used they used both in DarkSide 50 and they're planning to use in DarkSide 20K underground argon because it's more radio pure in argon 39. Argon 39 counts as one becquerel per kilogram. Okay, so with ton scale detectors, this is a very strong signal, and the depletion factor in argon 39 that was demonstrated in DarkSide 50 using underground argon was a reduction by a factor more than 1000. So impressive. To do this, they need to extract argon that has been found in a mine in Colorado. They will bring it to Sardinia where they will distill in a distillation column to remove other impurities and then checked in Spain and sent to Gran Sasso for the realization of the detector. So it's a complex system. And this is the sketch of DarkSide 20K, where we have from outside, we have the outer Vito. This cube, this red cube is at the outside is about 10 meters in size. The outer layer is filled with standard argon, while inside the cryostat there is the underground argon. Inside the cryostat there are two layers. In the center there is the TPC, and the layer between the TPC and the cryostat is used as a Vito, again for neutrons. This can be seen better here. So the TPC is quite large. It is 3.6 meters in size. That's challenging. It's made in acrylic, and this is also another challenge. The planarity. So when you go to these very large dimensions, the planarity is an issue. The planarity has an effect on the electric field and so on. So everything has to be checked very carefully. Sure. Becquerel is one event per second, one count per second. It's Becquerel and Becquerel and Earth are 1 decay per second, yeah. So it's 1 Earth.
There's 1%.
Yes, becquerel and earth are the same. Basically, you use earth when you are regular, and you use becquerel when you are Poissonian. That's my take-home message. But yeah, that's the point. So 1 becquerel per kilogram means 20 kilohertz in your detector, in a dark side size detector, 50 kilohertz. So now, yeah, this is the details of the TPC inside the cryostat. It has this octagonal shape, and the top and bottom of the TPC are filled with photosensors, just a detail of the Vito, where the PMMA is the acrylic layer, so you have the TPC inside and the Vito outside. The neutron can be captured inside the PMA and emit gammas that can be seen either by the TPC or the Vito. This is typical of the various Vito. They planned to dope the acrylic with gadolinium, that is the element in the periodic table with the highest neutron capture cross-section, but at the end it didn't work, so they will use the hydrogen naturally present in the acrylic. The photosensors are another challenge because they changed from the PMTs that are not so easy to be used inside the temperature of liquid argon that is much colder than the xenon. Plus, the silicon PM, the new photosensors that they are using, are very good in terms of radioactivity. Plus, at the very low temperature of argon, they also have a quite good dark count rate. Okay, any photosensors, I don't know how much you are expert of these tools, but it's a device that converts the light into an electron. Okay, and so this happens when there is light, but this happens also for thermal emission. So when you operate at room temperature, you have a very high rate of these thermal electrons that are extracted and get converted into the signal. At the low temperature, in particular of liquid argon, this is decreased, and so it works. You can see that you can do this also with the photo multiplier, but particular with silicon PM, you can distinguish very well the various peak of each photoelectron that you detect. This is done in a Sergi, where the Gran Sasso laboratory is present, and they will at the end fill the base, the bottom and top part of the TPC with these photosensors. At the end, the plan is to run the detector for 10 years, and you see the red lines are those of dark side. So depending on the fiducial volume that will be used, it will be close to the neutrino floor for argon. They also plan to have a even larger detector that is called Argo, but now they are very busy with installing the detector underground. Of course, the timing, the recent prediction I heard of filling the detector by 2028. Pardon? 27. Okay. 27, 27, 28. We will see. Why having an argon detector when there are already existing xenon detector close to this region? Well, first of all, it's important to have two targets. If we will ever have a signal of dark matter, it's crucial to have another detector, in particular with a different technology, both because the target will be different, and so also the kinematic of the interaction in xenon and argon will be different, but also for the different backgrounds, the different assumptions that are made in the detector. So the more different they are, and the best. So that's why we all think that it's extremely good that we will have soon this detector at LNGS to produce data. Now let's go to the xenon world, and this is the chronology of the xenon detectors in the last 20 years. We went from the 10 kilogram scale up to the 10-ton scale as of now. This is including the detectors of the competitors, for instance, in the past, where there was also a very important Lux and Panda X. And you see here now that it's important to increase the size, but it's not just a brute force approach, because in each step that you make in getting bigger, you also have to reduce your background. Otherwise, you do not gain as much as you can. Indeed, we can see it better in the plot here. This is the increase in size of the detectors, and this is a future detector. But correspondingly, we also reduced, in this case, the electronic recoil background by being bigger, because the center of the detector is cleaner and cleaner, but also by adding techniques to distill the xenon, the argon, so in this case the xenon, and to get a better signal. The previous generation of detectors is shown here. The size went from 50 centimeter up to 1 meter with 1 ton. That they have been completed by 2018. Xenon 1 ton was the first detector at the ton scale. So it was a massive improvements with respect to the previous ones. Also for us, we went from the Xenon 100 that was in a small box in a corner of LNGS to a new hall in Hall B in the Gran Sasso experiment. And also here I show some pictures because we can see basically all the ingredients that are needed to run efficiently an experiment. So in our case, the detector is inside this water tank. It's 10 meter by 10 meter. And the detector is here at the center, the TPC inside the cryostat. Just outside of the water tank, there is this building, 3-floor building with all the ingredients. Indeed, we have the cryogenics and purification system. So we need to keep the xenon cold and continuously purified. We have a xenon recovery system. Xenon is very expensive, so as soon as there is a problem, we need to recover the full inventory down into this ball that is constantly cold and pressurized to host the precious detector. We have the distillation column and the xenon analytics here. Now we have also a radon column on top of the radon distillation column in the 3rd floor. And then you need to acquire your data and analyze them. And this is done by the DAQ system here. Outside of the cryostat, there is the muon Vito. So the water is not used just as a passive shielding, but also to detect muons. So indeed, these are the details of the Vito, but we will come back to this in a while, also with the addition of gadolinium to the water to improve, in particular, the neutron capture efficiency. The summary of the previous generation of detectors is here. Basically, you see that in most of the parameter space, we have a liquid noble result. In particular, xenon, with xenon, Lux, Panda X, they dominated this region here. There was this result by dark side 50 with the S2 only result, plus also that was mentioned with the Migdal effect. We can also probe this region here, but of course, this is in the assumption that the Migdal effect exists. Graciela mentioned it yesterday. This is not yet proved, and also you have to compare apple with apples. Anyway, the previous generation of xenon detectors did a great job, and I want to highlight one point for xenon that, of course, I told you we want to discriminate between nuclear recoils and electronic recoils. From WIMPs, we expect nuclear recoils. But this doesn't mean that we throw out the electronic recoil events. They are simply in a different band that is quite separated, but they are still there. So if you manage to have a very low electronic recoil background, as it is the case, you can use this band to look for a signal. There are models that predicts dark matter, but also axion-like particles interacting with electrons, and this was used indeed in xenon 1 ton to look for any possible discrepancy with respect to the background model. And indeed, in 2020, we had this so-called xenon 1 ton excess in the electronic recoil channel. That was this low energy bin here between 1 and 7 keV, where we had an unexpected excess. The point is that we checked the background model in various ways, and we couldn't find any clear explanation. At the end, it was appealing because axion-like particles, but also solar axions, anomalous magnetic moment of the neutrinos can have an effect in this region here, but also tritium. Tritium was a background that was not expected, was not considered in the background model. At the end, it turned out that it was one possible explanation. When we had this result, the experiment was already dismounted. We were commissioning xenon and ton, and so we dedicated the first search in xenon and ton to prove the effect. So experimental particle physics is there to check any signal. And so with our improved detector, we we made the same search, and basically there was no sign of this excess. And so this was, so the only explanation at this point was that the effect in xenon 1 ton was due to tritium. Okay, so less exciting than axions, of course, but it was, to me, a nice way to see experimental particle physics at work. So where you make something better because the background in xenon and ton was much smaller, a factor of 5 smaller than 1 ton. So a signal could have emerged much better. Indeed, there was no indication of it, and so the axion potential signal was neglected, and the only surviving explanation was tritium. By the way, in xenon and ton, due to this possibility, we also had cleaning, also a baking and the cleaning more focused on removing any potential trace of tritium. By the way, just to give you some numbers, the tritium responsible for this excess in 1 ton was 10 to the minus 25 with respect to xenon, if I have it on top of my mind. So we are sensitive to such a tiny amount of tritium. So it's not a tritium contamination. We call it trace of tritium, really a handful of events. But when you are sensitive, you can go also in these regions. Pardon? Well, the energy spectrum was the key point. Tritium as an endpoint has 18 keV, and the shape of tritium was compatible with what we saw. So, and also, tritium can be inside water, so being part of hydrogen, can be inside water and can be emanated from the materials. So that was a possible explanation. Of course, it was likely to be tritium. That's what we concluded. Now let's go to the current generation and then to the future of this kind of detectors. Currently, we have Panda X with 4 ton of xenon in China. LZ, yesterday we had a presentation by an LZ student. LZ is in the US. It is currently the largest among the 3 detectors, Panda X, LZ, and Xenon. And the scheme is the following. It's inside a water tank. In their case, the water tank is used as a passive shielding. The cryostat is surrounded by this neutron veto that is made by acrylic tanks filled with liquid scintillator doped with gadolinium. So you see that the ideas are slightly different from one detector to the other, but the concept is similar. So big water tank, something properly done to detect neutrons, and then the cryostat with the xenon inside. Recently, there was this result from LZ that is currently the best in the world. They have this very nice limit, also with an under fluctuation with respect to the medium sensitivity. When you have these bands, what you are saying is that the sensitivity, so the power, the performances of your experiment allows you to explore this region here with 68% the green area and 90 or 95 the yellow area. And then the result that you obtain in that set of events is what you draw with in this case with the black line. So this is the meaning of this kind of plot. This is the PRL in 25 of the LZ collaboration with this beautiful spectrum. Here is what is how you usually present your event. This is the plane of charge versus light. So S2 versus S1, that are the 2 informations that we have at the end in the TPC. And basically, this is the electronic recoil band. The WIMPs are searched in this region here. And so basically, there was no indication of events above the expected background, and this gives the limit. So now I will move to xenon and ton in the last 20 minutes of this lecture. It is since this is not a review, this is a school, I decided to talk more about xenon because is the system that I know better, just to give you examples. So it's not to be unfair with the others. The results have been presented, but now let's see how we improved from xenon 1 ton to n ton. And these are the main upgrades. So we had a larger, this is paradigmatic for any step that you made. So we increase the TPC. This is the first point. And for instance, with respect to xenon 1 ton, it was 3 times larger in the sensitive volume. Also, the number of sensors increased by a factor of 2, roughly. Now we have about 500 photosensors divided by the top and bottom of the TPC. Together with this improvement in mass that aims to increase the exposure, there were other systems that have been added. In particular, we added the cryogenic distillation column against radon. In the previous version, we only had it for krypton. The one for radon is more complicated because it has to be run continuously to get rid of radon that is constantly emanated from the various materials. Indeed, the improvement was connected with an improvement in the purification system. Previously, it was done only in the gas phase, so it was slower and less efficient in a way. Now, with the liquid purification, we extract directly the liquid, we send the liquid to be purified in the getters, and so on. So everything runs more efficiently. Finally, we added the neutron veto, and this was done in particular by the group led by us, the INFN groups, and so I will show also something about this. Now, the TPC. This is a sketch with the photosensors here ready. from the very beginning, we had a problem with the electrodes, and there was a short between two electrodes at the bottom that due to this, we had a smaller electric field in the drift region. So this affected the drift velocity, for instance, and so also the time needed to collect the electron. On the other side, it improved the light emission. So anyway, at the end, we decided to go on because we could take good data, and I will show you some results in a while. About the cryogenics, I have already mentioned the liquid purification in addition to the gas purification. That meant adding two dedicated pumps and so on. But what we can see is here. So this is the electron lifetime. I remind you that this is the parameter that tells you how pure, how clean is your xenon in terms of electron collections. The higher, the better. This was the situation at the beginning when we only ran through the gas purification. As soon as we switched the second gear of the liquid purification, this is the clear improvement in the electron lifetime that now is more than 10 milliseconds, 20 milliseconds. Keep in mind that the TPC, our TPC right now is 2 milliseconds long. Okay, so 10 milliseconds is well enough to collect properly most of the electrons that are produced. So this was an extremely important step. The distillation, in addition to the krypton column, we added the radon distillation. And so this is used to get rid of radon, and this was done in the two phases of liquid and gas recirculation, and basically the results are here. With the new system, we obtained an important improvement in background, but also with the full power of the circulation through the column, we went below 1 microbecquerel per kilogram. Why this is important? This is important because with this radon level, as I mentioned yesterday, we went to a background induced by radon compatible with the one induced by solar neutrinos. Here are the PP neutrinos, so the most abundant and lowest one in energy, that produce electron scattering, elastic scattering of electrons. And so this means that we are almost done, not fully, but we are almost done. We need to, for the next generation, to decrease further the radon level, but we can do it by a factor 4, 5. After that, anyway, neutrinos are there. So this is an important result that can be also used to study solar PP neutrinos, and this is what we hope to do. Now, coming to the neutron background, we had this neutron veto. In our case, we couldn't use liquid scintillator at LNGS for environmental restrictions. And so we decided to use water. In particular, after a first run with standard water, demineralized water, we added gadolinium in the system. The idea is that the neutron is dangerous when it makes a single scatter, because it has to be like a WIMP, okay? But if the neutron makes a single scatter, this is true for any neutron veto. If the neutron makes a single scatter, it means that it came out, okay? It cannot be there. If it ends inside, it will be captured by xenon or argon, and it will be seen. To be dangerous, it has to be out. So what we do is to stay out and check it as soon as it comes out. This is done through neutron capture, either in hydrogen of the water or gadolinium. The thermalization happens very efficiently with the protons of the water. As soon as there is this capture, the energy released is of 2.2 MeV for neutron capture in hydrogen. And For gadolinium, it is of the order of 8 MeV, so even better. Why even better? Because we have to go back to yesterday. Natural radioactivity ends up at about 3 MeV. So while this line is inside the natural radioactivity, with the addition of gadolinium, you are completely outside of it. So the signal is even clearer. This gamma makes Compton scatters through with the electrons, and this produce Cherenkov light. Cherenkov light is detected by photomultipliers. This is the idea, and this is a sketch of the system. I also added some links to the making of the TPC and the Vito if you want to have fun. This is a picture of the detector where the white panels are made of expanded PTFE that again is a very good reflector for the Cherenkov light that is UV and blue light. We doped it with gadolinium, putting salt inside. It's gadolinium sulfate octahydrate. As soon as you insert the gadolinium, you have to be clever in the purification. Because why purification here? Again, we want to see Cherenkov photons, so the water has to be as very transparent. This is even more important when you add a salt in it. And so the system cannot be used the standard deionization, because in this case you will remove the gadolinium that you put in, but you have to make a pre-separation with these nanofilters. This is a technique that was tested in Super Kamiokande, where they also have gadolinium, and in this way we can clean the gadolinium depleted part and recirculate everything. So we managed to improve the neutron capture efficiency by a factor of 2 with the addition of gadolinium. Gadolinium has two effects. One is to reduce the capture time, depending on the concentration. With hydrogen, it was about 200 microseconds, and half of it with gadolinium. Plus, you shift the energy from the 2.2 peak of hydrogen, adding a shoulder at 8 MeV. Of course, hydrogen is still there, so now we put a small amount of gadolinium to start with, and so we have the presence of both the peaks. But at the end, we improved by a factor of 2 the tagging efficiency of against neutron, and so the background. That was very good. We went on taking data, and this is the WIMP search that we published this year, that is not as stringent as the one of LZ, but again, also in this field, it's very important to have many detectors looking at the same parameter space. So to do better, how can we do better? No, let's first talk about this before doing better. With the current detector, we had this very important result searching for boron-8 solar neutrinos. Okay, this was the first detection of the coherent scattering of solar neutrinos in a dark matter detector. Before this result, all the coherent scattering results were made with artificial sources, spallation, so pion decay. The boron-8 neutrinos arrives at 15 MeV, and so they can induce a signal at the very end of the low energy of xenon detectors. Indeed, to detect them, we lowered the threshold, in particular the threshold in S1, that is the more important, from 3 to 2 photoelectrons. This, of course, improve the efficiency to detect the signal, but also induce a new background that is that comes from accidental coincidences. Anyway, we kept it under control, and at the end, we obtained a signal that was in agreement with the predictions of about 12 events. So here are the results. And so this was really an important detection. Again, the first one from a natural source. And so also the first situation where we really are in the neutrino fog, because we are seeing the effect of solar neutrinos. Just a few final slides. Why we want to do better. So here we can understand better the situation. With xenon and ton, we have a better electronic recoil background than LZ. This is seen here. This is the line of Anton, and the orange is the one of LZ. Despite this, the performances of LZ are currently better. Why? This is due mostly to the discrimination. Since we had this problem with the electrodes, the discrimination between electronic and nuclear recoil is better in LZ rather than in xenon 1 ton, because with a lower field, you cannot separate very well the two bands. So this means that even if we start with a smaller amount of electronic recoils, then the fraction of them leaking into the signal region is higher. And so at the end, we decided to change, to replace the electrodes, because you can see it here from the simulations, but they are tested. This is the field where we operated, and you see the two bands touching one to each other. If we go to the nominal field that was 100 volt per centimeter, the two bands are very well separated. So after a few years of taking data where we get the most from the current status of the detector, we decided to upgrade it, and just to give you a feeling of real life from an experiment. So we prepared new electrodes. I'm just flashing out these slides now. We drained the water. That is quite an operation. We entered the water tank. We removed the neutron veto. We put back everything from around the cryostat. We built a clean room around the cryostat, and this was done since April of this year. In this way, with the clean room, we could open the cryostat and get access to the TPC. In particular, at the bottom of the TPC, we found the culprit. That was this, you can see a wire here touching the two electrodes, and that was the responsible for the short. We replaced everything, and now we tested the new electrodes that are working properly. We closed everything, and in the afternoon, I will go back to Gran Sasso to go on with the reinstallation of the detector, because now the cryostat is closed. We started rebuilding the neutron veto, and by the end of the year, we plan to go on taking good data. Yes, in the 5 minutes, I will flash the next step. I mentioned mostly of xenon and ton and LZ that are currently good competitors. The two detectors are similar from one side, so the technique of the central detector is the same, but there are differences in many ancillary systems. Anyway, we decided to go on together to build the new detector that is called XLZD, with a quite a strange acronym. We will replace it at some point, who knows. Anyway, so this is to have the next step, joining forces between xenon and LZ. That will be a full observatory looking for dark matter, but also for neutrino-less double beta decay. We couldn't mention it in this kind of lectures, but also for solar neutrinos and supernova neutrino studies. So it will be an overall detector. And again, any time that you increase your sensitivity, you are also ready to see the unexpected. Okay, we discovered with 1 ton the longest decay in the universe, for instance, of xenon 124 and so on. Anyway, the scale of the detector is to be at the 60 ton of xenon in the active part of the TPC, so roughly a factor of 8, 10 with respect to the current detectors. The size will be 3 meters. Given the density of the xenon, it is still possible to build quite compact detectors, also with this high mass, and the plan is to reach the neutrino floor. This is still open. Indeed, as of now, there are many possible sites that we are evaluating, mostly Gran Sasso, Surf, where LZ is, Bulbi, where they are hoping to have a new laboratory, or Snow Lab. So all the 4 laboratories are under scrutiny, and the decision will be hopefully next year. In Gran Sasso, it will be in All C between Dark Side, that is this red cube, and Legend 1000, that will be in the last final part of the all. Here in the middle, we may have XLZD. And so the goal is to go on exploring the parameter space down to the neutrino floor with the next generation detector. Here is still named Darwin, but it's XLZD, and dark side will also be close to that region. So with this, I thank you. And here there is xenon in this periodic table, but be careful because there is also radon very close. And so we hope to find dark matters sooner or later. Any questions? Yes. Of the TPC? This one? Yeah, these are 7 PMTs that from the very beginning didn't work. So among 500, we have 7 channels that for various reasons were not available. There is some redundancy that you keep. Of course, the best would be to have all of them properly functioning, but we can survive also with this rate. Yes. So you said we know the mass and we know the coupling. I admire your. Okay, no, with the in the final plot that I showed you, we will go down to the neutrino floor. So we will explore all the parameter space that we can do, and in that parameter space there are models that predict WIMPs. So if we do not find them, they will be ruled out. Then this means that either WIMPs have a smaller coupling, but it's hard to go there with the current ideas of detectors. We need directional detectors. I don't know. That's tricky because of the needed mass, or we have to invent other ideas. Yes. There is a question also here. So the photomultipliers can see the single photoelectron. So the threshold doesn't come from the photosensors themselves, but more from the overall system. Basically, for nuclear recoils, our threshold is at about 3-4 keV. So we can see a nuclear recoil of 4 keV. Yes? Photons in the range of EV. But you mean photons? Photons, not energy deposits. Photons. So infrared. Okay. I cannot answer right now, but yeah. Okay.
The highest mass, I think, low threshold sensors that exist, and the silicon band gap is 1.2 dB, I want to say. If you want to go even lower than that, I don't think we currently have a bulk detector, but SNSPBs are one way. You could go even lower and give up PESs, MKIT, there's a lot of development, but at the 1 EV, I think it's pretty strongly dominated by silicon, and germanium is a bit higher, right? But how to measure photons and
Photons and EV and
yeah, this is even lower than the EV, right? This is the, oh, yes, photon, not photon.
The question was about photons.
That's-
Okay. Mhm. Remember.
cannot do a comment
Ah, okay.
on what was asked. So, an electroweak dark matter, so in the sense charge under electroweak interaction, as most of the candidates are, they have the luck of being above the neutrino floor. So in this sense, what Marco showed
There was even a
is,
plot.
is very optimistic in the sense that
There's this paper.
By Bloch and Bloch.
By-
Nicola.
yes.
Yeah.
Yes, so most there was another one. Most of these candidates lie above the. So what I mean by neutrino floor is the standard neutrino floor, so nuclear recoil. So they are within the what Marco called the neutrino electric. Let's say that's the sensitivity depends on the way how good we are to reject electron recoils. But is another story. So
But he had an actual plot with the candidates, I think.
yeah, I mean, this plot shows that it's within your lifetime you would.
And except the one who's collecting that.
Other questions? I have a good question about the resolution with two-phase cells that calculation that is cell velocity. But velocity is dependent on T. So how do you get a resolution from that?
So the velocity does not depend on z. The velocity is fixed. It's fixed by the electric field. So since the drift velocity is known, and you can measure it because you know the end of the TPC, you know where the cathode is. So your electrons will come at most from that position. This is the reference point. Then you simply scale the time with the yes, yes. Right. So the assumption is that uniform field, uniform velocity. Of course, we have a detailed map of the electric field inside the TPC, but in the center, the uniform assumption is quite correct. Okay.
Questions? If not, let's thank Marcus.
Thank you.